All right, welcome to Game 2005. That's game physics at George Brown, and in the fall 2018 semester, we are week, it says lesson 1, that's wrong. We are week 2, I'll update that. Part 1, which is, we're gonna talk about limits and derivatives today. And just as I mentioned earlier to people here in the class, assignment 1 should be released now. So if you take a look at Blackboard, there should be under assignments, there should be a section that says assignment 1. I will talk about the assignment in class, in lab with you. So during lab this week, I'll go over it and I'll go over it in detail. I'm not going to waste time talking about the assignment here. All right, so limits and derivatives. This is the big one. Let's talk about that. So again, you know, there's studies, we have patterns in mathematics, right? And what we want to know is, you know, we have some information, a lot of times partial information, and we want to gather or determine other information from the information we have. And we also know that there's relationships between things like velocity, acceleration, position, all these kind of things. And that, my friends, is what this limits and derivatives thing is all about, because for physics, all you really care about is position, velocity, and acceleration, right? Well, not all, but a lot of it. All right, so we want to be able to kind of, you know, implement linear movement on the screen. We need things like, and especially things like with your game, we need things like some net acceleration. So what does that mean, net acceleration? It means like, okay, I have all these forces, right? And we're going to be talking about that more as we get into physics, right? In a game, I'm going to probably have all the forces in variables. I'm going to have gravity in a variable. I'm going to have how many pixels per meter in a variable if I'm doing a 2D game, right? Because I want to create my relationship or ratio for the game, right? So imagine if I have a screen that's 640 by 480, very small, or a larger screen size, you know, 1920 by 1280 or whatever it is, and I say, okay, I want some kind of relationship between meters and pixels, right? Because you want to kind of create some realistic movement on the screen, or something that looks more natural on the screen, right? And the way to do that is to have this pixels per meter kind of thing, because gravity and physics and all that kind of stuff works in meters a lot of times, right? Or some unit, all right? You want to have some, you know, relational unit that it's going to work in. And anyone remember what the acceleration due to gravity is? You should know that. Yes. 9.81. I probably would even go with 10. You know, why 10? Why would I not be exactly 9.8? Because chances are your game is not, your players aren't going to know. In this course, we're going to keep with 9.8 just for calculation purposes. But in the real world, when we do games, we might go to 30. And I'll tell you why. Because it tends to float. Whenever, I don't know if you ever tried doing a thing where, you know, you try and do 9.8 meters per second. The characters, when you're doing a platformer, tend to float a little bit more, right? I want those characters to drop like a stone, right? I want them to like jump up and go down again, right? And in order for you to do that, you need more, either more mass, right, which is something you can do. But then you need, if you have more mass, you need more force, which is kind of a bad thing, right? Because it can mess things up. I need a higher acceleration due to gravity, which means I might use 30, right, instead of 10, which is really weird. But anyways, so those are the things. So acceleration, or position, velocity, and acceleration are the 3 things we care about when it comes to moving. So what if we don't have acceleration or velocity? We want to calculate it. And sometimes what happens is we don't have those numbers because something is in motion, where you have like, you have an object, or whether it's a vehicle or an enemy or a player, and it's in motion, and you want to be able to calculate instantaneous velocity or instantaneous acceleration or whatever it is at any point in time. And we need some ways of doing that. And so we're going to say a lot of the rate of change, right? And when we hear about the rate of change, that means that something is moving or changing. The number is not staying the same, right? So if I start thinking about position, right? So I have a position. Let's say, for example, in a particular point in coordinate space on the screen. Okay, let's talk about global space, global coordinate space. Somewhere on the screen, I've got my position. And then I want to calculate, you know, I want to get to another position on the screen, and, you know, I want to calculate the velocity that's required for me to get from point A to point B, right? If the velocity is steady, right? So there's no change, then there's no rate of change. The rate of change is 0, right? Because we're not changing anything. Velocity is staying stable, right? However, if the velocity is going up, hence accelerating, right, then we have a rate of change. And we can relate velocity to the rate of change of position as well. So we have position. I have a point in space in the global coordinate system, and I have a point in another place, and I'm changing position. So therefore, there's a rate of change of position. How fast do I change position? That's velocity. How fast do I increase velocity? That's acceleration, okay? So rate of change is, in your minds, what you should start thinking about when it comes to derivatives and limits. And here we have the position at time t. Okay, so we're saying, please don't be afraid of the variables, and if you have a question, please let me know. So we have position, and if you think about this, we can calculate the instantaneous velocity at a particular point in time. Instantaneous velocity means just a slice. If I had a time slice, and if time t was created in frames, like frame rate, right? And again, average frame rate for most games, at the bare minimum, is 60 frames per second. So at that time slice, where time t is 1 frame, right, as an example, or 16.666 milliseconds non-terminated repeating forever and ever, right? 1 frame, then we could say that the velocity in this particular case, if it's t squared, right, is a exponential velocity. It's going to, something, or the position is moving in terms of this exponent graph, if you will. And that's why I talked about graphs last week of Desmos and all that stuff, so you can actually plot out or see the motion in terms of space, of where the new position is going to be based on the velocity, right? So here it says, what is the instantaneous velocity of the character at time t is equal to 1? Of course, that would be 1, right? At time 1, it's position 1 unit, whatever unit it is. Most likely it's meters. If you're programming in Unity or I think even in Unreal, the unit measurement is meters, 1 meter. If you're plotting stuff out in Blender, okay, and I'm just going to use a visual aid here. This is not because I want to teach you 3D modeling or anything like that, but I'll bring up Blender again. It's one of my favorite tools to use because it's visual, right? So it's like students are going to sit there and go like, okay, I cannot understand. I can't picture it, right? So in other words, here with Blender. Right now, I'm in the scene at a particular position. I'm at 0, 0, 0 in Blender. So X, Y, and Z is all zeros, as an example. One good thing about Blender is you can go to a 2D looking camera, right? So and by the way, Blender is a free open source 3D modeling tool you guys can download. If you go to blender.org. So again, I have different viewpoints. I can go to the front, I can go to the side, I can look at it from the top or whatever. And I want to look at it from the top in this case because you can see that up for Blender is the Z axis, and X and Y is on the top. So I'm looking at the top view. I'm still looking at it from a perspective camera, which is going to skew the view that you're going to see here. It's still probably very difficult for you to see. I'm just trying to see what you see compared to what I see. But if I go to, this is orthographic view. Just a second, let me just turn the lights down. Maybe that's a little better. Yeah, so if you look at it from an orthographic view here, right, it's literally this grid mark, and I know it's kind of hard to see, but there's grids on this screen, and the grid is in 1 unit measurements, right? So again, if I move, so right now I'm looking at, I'm just going to do, kind of move this thing from one place to the other. So you notice that the dimensions of the cube, and this looks like a square right now because we're looking at it from a 2D perspective, right? But it's actually a cube, is a 2 by 2 by 2 cube. That's what it is, right? So one thing to note, whenever you do any kind of game development, you have a transform, right? And in time, you have a location, rotation, and scale for any kind of thing that you do, right? And it doesn't matter whether you're actually doing things in 2D or 3D. You have these 3 elements or properties of an object, right? And in Unity, all objects, I'm just talking about Unity, for example, but it could be any game engine. Every game object has a transform, whether it's a camera, whether it's a light, right, in the scene, whether it's a player or whatever it is, right? And if you think about it, if you did your 2D games for game production too, and some of you did that as well, you might have had these properties. You might have had location, rotation. You didn't care much about scale because usually scale is 1 for the most part, right? But you can modify things on the fly when you do that kind of thing. So again, enough about game stuff. I know it's a little bit of a side, but if I want to move across the x-axis 1 unit, okay, so now, okay, actually, did I move that? Yeah, that's the y-axis. Let me just undo that. The x-axis across 1 unit, there we go. You can see that it actually moved 1 and from this point to this point. And this is in global space, so global coordinate space, right? And again, my object was in the 0, 0 position with the registration mark, if you will, or the focal point, the rotation point, if you will, whatever you want to call it, center of mass in the middle of the object. Again, if I looked at this from a 3D perspective, you can see that it's in the exact middle of the object, right? And that's how we want to treat all of physics when we go forward in this course. Everything is the center of mass. We're not going to play games in terms of I have an irregular object that's a little bit gooey on the top and stuff like really weird stuff that'll really mess up your calculations. Straightforward. It's some kind of primitive object. It's a cube. It's a sphere. It's something else. It's a car, you know, something like that. And it's a hard body object. It's not a soft body object that has, you know, gooey collision or anything like that. Elasticity, not too much. And the center of gravity or whatever is in the center of the object, center of mass. Okay? I point this out to you because when the stuff I'm going to be talking about later, when we get to start visualizing what we're going to do, there's 2 ways to do this visualization. One of it is to graph it. The other one is to actually use a tool like Blender or something like that and to do a simulation. And Blender is great from a simple animation perspective. Will I teach you Blender this semester? I will talk about it, but there's no time for it. If you really want to learn Blender, there's all kinds of tutorials out there. Let's talk about limits. So think about this as I want to get as close to a position as possible without actually, you know, I want to kind of calculate the closest I can get to an object, right? So that's what it says. If I move some input x close to some value x naught, x2, then what will happen to the function f of x? And f of x, by the way, in your mind, from a functional perspective, because you should think about yourself as y. F of x would be like y, right? Because the function of x, right? If I put x as a parameter inside the function f, right? And I return a value, which is what I'm doing. I'm returning a value for y typically because there's a relation between when x moves, what happens to y, okay? And z if you're manipulating things in 3D space. So I want to get as close as possible to some value. And when would this come into play? We can say that, and here's the definition, that the limit of f of x as x approaches a equals L, whatever L is. And we write it like this. So when you write stuff, and on the test, you'll see, it being written like this with lim for limit. X is some value, some parameter x, and then there's an arrow, and then as it approaches some other value, a, right? It could be whatever value that is, a negative number, a positive number, 0. And then we want to pass in this value, f of x, right, into f of x to produce some other value, L, depending on the formula. Okay? So again, like it says, we can we can approach L, some arbitrary, distance closer to L, but we'll never achieve L. It's almost like we're going to approach it because if you think about this, if we take a real number, all right? So if I have going back to Blender again, right? Now Blender has limits in some ways too, because Blender is a 3-dimensional program that we're using in a computer. And computer with real numbers, it's not an infinite. There's not an infinite amount of real numbers we can represent with computers. I mean, we can try and represent a very long number, but there's going to be a limit, literally, to how accurate we can be with a computer program, right? And I'm sort of shifting to to perspective mode here, right? So again, in the numeric transform, I can change the value of the number to something very, very small. Like, for example, I can say something like, well, I want to move on the x-axis 0.000001. And you're going to see that there's literally no change. In fact, Blender just ignored it, right? Let's go for another number, 0.001. And again, I put it in, but no perceptible change, right? And that's what's going to happen with limits. You're going to approach a particular thing, but you may not actually get there. And when would this actually be bloody useful at all, right? Collisions. Sometimes what happens is, you want to kind of calculate the distance roughly between, your player and an enemy, and you want to approach collision, but you're not going to actually get there before you actually register a collision. And sometimes that's because it's good enough to do so. So limits can help us in there. But the most part, the reason why we want to talk about limits and derivatives in the beginning is usually to understand how calculus was derived, okay, more than anything else. Okay. So here's, the second theorem. Okay, so we have this theorem, which is direct substitution. So if f is some kind of polynomial or a relational function, so we have some kind of weird function, x squared as an example, that's what f is. And a is the domain of f, is in the domain of f. So somewhere in there, it makes sense. Like, so it's not something outside of the domain. It's not an imaginary number. It's not something else that's on the z-axis as an example, if you're talking about x and y. Then we can say that the limit as x approaches a for f of x is equal to f of a. So what this means is we can literally take the value of a and sub it into our equation. That's what it means, okay? It's very simple. Don't worry about the mathematical crap for now, okay? Like, literally, when you look at this, you look at it and go, hey, if I have an equation, x squared, and if I have a limit as x approaches 0, I take my 0 and I sub it into the equation. That's what it means, all right? So there's things that'll bug us when we do that. Things like we have to watch things like dividing by 0. That's not possible, right? We'll get some really weird things like either infinity, positive or negative infinity. We might get something that's undefined if it's 0 over 0 as a good example, right? Something like that. The square root of a negative number, we could get that when we sub things in. Or the log, natural log of a 0 or negative, right? And those are the three cases we don't want. We want to make sure that this might be undefined if we come to one of these cases, okay? So sometimes we have a formula and we sub in the number, let's say 1, and then that'll cause some kind of real weird problem where it cannot be solved, okay? Let's continue. So here's some limit laws. By the way, I will put these on your cheat sheet, so you don't have to remember any of them, right? But I want to talk about some of these because these are basic things, okay? So again, you have the limit, let me just go a little bit closer, as x approaches, sorry, the limit as of x approaches a of f of x. So there's two functions. I have f of x and g at x, okay? Now I want you to think about this. It's almost like if I was going to write a function in C++ or C# or Java or whatever the language you choose to write your game in, hopefully not Java, or C#, unless you're doing Unity. Hopefully it's C++. From a performance perspective, you get two functions that it accesses. So I go to the function, and that function calls two other functions. I want you to think of it this way, okay? And then when those two functions, I'm adding the results together, and I'm returning that result. That's what this is. That's when you see this kind of notation, if you will. So it's like if I say the limit of f as x approaches a of f of x plus g at x, it's like saying I want to take the limit as x approaches a of f of x plus the limit of x approaches a of g at x, and those things are equivalent, okay? Same thing with the negative. If I subtract something, now this is interesting. When I multiply things, okay, this is interesting. So as x approaches a of c, whatever this scalar is, right? I have some kind of scalar, this number, and then I multiply it by f of x. It's like saying I can take the c out. I can take that multiplier and remove it from my limits, and then calculate the limit as x approaches a of f of x, and then multiply the result by c at the end. It's the same thing. There's a commutative, way of doing things. Okay. How about if I have two functions that I'm multiplying? So x approaches a of two functions that I'm multiplying together. You can also say that I can do each function separate and multiply the results together. All right, so that's basic stuff. And there's some other weird things, okay? So here's something. What about if you have some function like this? So limit as x approaches of a and of c, some constant, right? Well, that is always going to end up being the constant because x has nothing to do with the constant, right? And sometimes you get that weird, result, right? And the same thing goes with, if I have the limit of x as x approaches a of x, then it's just going to be equal to a because there's no, if x is just a linear function, then you're going to get the linear function back. Yeah.
Right. So the limit x to a, that symbol, that actually doesn't have functionality. It's more like just.
You say, I want you to say it like this: the limit as x approaches a. So x a number, whatever that variable is, as it approaches a value, because that number could increase, right? So right now we're saying that we don't know, we can't calculate every single number between, let's say 1 and 2. We can calculate some of the numbers because there's, especially if they're real numbers, because there's, an infinite amount of numbers between 1 and 2, if you think about it, or 0 and 1. But as it approaches that number, we can use the limit to kind of calculate the potential end result. Why are we doing that? Because think about this, right? Sometimes a problem in mathematics or in computer science is unsolvable with the current technology that we have, all right? However, we can approximate what it would be like with fair accuracy, and that's what limits allow us to do. We don't know exactly what the result is going to be, and sometimes it's impossible to get there because there might be an imaginary number, something weird that we can't calculate. For example, I don't know, a quaternion rotation, as an example, in three-dimensional space. We don't exactly know what's going to happen, right? But we know that it's going to approach this value, and it's good enough. And that's what limits kind of approaches. It kind of gives us a value of, we can't calculate every value, but we can pretty much say that as it approaches this number, we're going to get this result. And that's what limits are for. All right, so here's another one. We have a exponential function where x approaches a. Then we're going to say that whatever that exponent is, we're going to just sub in a, and it's going to be to that exponent. Again, where n is a positive integer. And the reason why it says that is, of course, if it's a negative integer, weird stuff can happen, right? It may not be the exact same thing. And there's other ones. I'm not going to go through all of these, but the reason why these are here is to help you solve potential problems. And I want you to refer to this page. We're going to probably do that today in lab, where we want to solve a problem, and you might have, different identities that we're going to be using to solve the problem, right? Because, and again, I don't expect you to remember any of these things. I've been able to look. It's almost like a lookup table for you, okay? Okay, I have this problem. What do I do? This one. That's it. That's really what I want you to do. That's simple. All right. So here's something. Here's an example. I want to talk about this in class. We want to find the limit as x approaches -2. Okay. What would happen if we just subbed everything in? Now this looks like really long, puzzling equation. But remember, we have all these things. We can split this equation up. We can do a bunch of stuff because we know that one part of the equation, another part of the equation, when we separate them and put them back together, it's the same as doing it all at once. So what would I do here? Any ideas? So let's think about the bottom part first. If I go to the -2, so 2 to the -2, so some negative exponent, right? That might be good. I can probably find a value, right? And then I subtract -7 times -2, right? So that'd be a positive number, whatever that would be, plus the cos of -2 pi, right? So I could just literally sub in and hope for the best. So what is the cos of -2 pi? Remember we talked about cosine before, right? It starts at the top. And so if I go to, to the left, I go down, what is it? It's 1, right? Okay. And to prove this, again, I'm just going to use Desmos to show you this kind of stuff. So here's Desmos. So if I say, -2 pi, right, which is this value here. And if I put that, if I wrap quotes around it, so if I wrap quotes around that, so the quotes of negative 2 pi, and if I put actually something like x pi in there, you can see that because we don't know what negative number it's going to be, right? And if I actually, or let's call it a instead of x, so we can make a slider. So here's a, and we're going to make this slider a positive number because we want to make it more negative, right? Where x is equal to this number. You can see that the number is going to slide now. Where I move, it's going to kind of oscillate between one side and the other, okay? And this is a different way of representing this thing, okay? You can also look at it with y, right? Where y is going to oscillate up and down, right? This kind of thing. It's going to move back and forth, right? If I put it back to negative 2, I'll make this x. So we'll just make it nothing. And if I put something like negative x pi, I get rid of this. And if I just kind of zone in here for a second, you can see that when x is 0, y is 1. And when x is minus 0.5, y is 0. When x is minus 1, now this is, remember, this would be like, instead of minus 0.5, if you think about what this is, right? Because this goes to, so this is 0 pi, right? This would be 0.5 pi, this would be 1 pi, this would be, 3 over 2 pi, and this would be 2 pi. So we're, when cos is negative 2, as an example, then when x is negative 2, then y is 1. And negative 2 would be like negative 2 pi in this particular case, right? So you have a 1 value there. And again, I'm bringing this up to you because it's good to, if you can't remember cos and you somehow don't have a calculator at some point in time in the future, you can always figure stuff out with cosine and sine by knowing where the cosine graph starts at the top here, as opposed to sine, which starts at the 0 point. All right, so if we know then that cos of negative 2, right, negative 2 pi is 1, so we have 1. And then a negative 2 times a negative 7, again, I'm just taking each term separately. A negative 2 times a negative 7 is negative 14. Negative 14 plus, again, a 1 is negative 13, right? So that we can figure this out, negative 13. And then what is 2 to the negative 2?
Actually, we have a minus sign.
Yeah.
For the 7x, so that's going to be plus 14.
Negative 2 plus negative 2, correct. 14 plus 1 is 15, sorry. And then plus thank you. It's early for me too. And if you have this 2 to the negative 2, what's that? Sorry? 4, right? Is it 4 or negative 4? 1 over 4, right? Because it's a negative sign. Anything there. So 1 over 4 plus. So do you have a 0 at the bottom is my question. No. Do you have some funky thing that, that you're going to have that's going to stop you from calculating the limit? No, not in the bottom. What about the top? So again, a negative times x to the 2. So negative 2 times 2. So negative 2 to the power of 2 is 4 with a negative, minus 4. So 7 minus 4 is 3 as an example. And then a square root. How about over here? Do we have a problem over here? Negative 2 plus 6. No, we can probably calculate this. This is 4, right? So that's 2. And then minus 9. So some kind of integer over another integer, I think we're good. And that's how I would approach this one, because there's nothing that's going to stop us from subbing in our value, whatever that value is. And our value, as x approaches minus 2 would be the value of a that we've seen before, right? So we take that minus 2 and sub it in. That is the simplest level. Okay, that's level 1. Yes?
Aren't there some cases, though, where the limit is not the same as the value at that point?
Yes.
Because you might have a function which is, smooth and continuous, and then there's one point where it's different.
Yes, and that's where we have discontinuous, or somehow the value is 2 points. There's a positive and a negative because the actual function, the graph is separated.
Oh yeah, the limit can be
right?
different from both directions, like as you approach dividing by 0.
And we'll talk about that as well. All right, how about this one? Can we solve this one? If I take 3 and sub it into this, what am I going to get on the bottom? This isn't solvable in this way. What do I do to solve this problem? No, that would be great if we could do that, but that's not the answer. Yes? okay, so the answer is I have to simplify the top. And how do I do that? I use factoring, and I get a difference of squares, right? So what this means is I need to factor the top, and I'm going to see if I can do this in class this time around without taking too much time. I tried to do this throughout the labs, and it was kind of worked out okay. But it's like saying something like this. I have an equation where I have x minus 3 at the bottom, okay? And at the top, I want to find something, I want to factor. So when I start factoring, it's going to look like this, right? I have two brackets, right? The first bracket, I'm going to use something called FOIL. I'm going to try and multiply the first terms by the outer terms, and then the inner terms, and then the last terms, and then add them all together, right? So it's like this. It kind of goes x. I know x times x is going to be the first term. Oops. Can I move this thing without making a mess? Okay, yeah. And then it's going to be x, and we'll just say plus for now, plus something, and then there's going to be x plus something else, right? And that's what the factoring thing looks like, right? So what numbers do I, x times, take the first term, x times x, that's x squared. And then what numbers, add together to get a minus, or add together to get 0 and multiply to get a minus 9? Don't answer. I want someone else, please. Because yes. I know you know the answer, okay? Positive 3, negative 3, you said it, the difference of squares. That's what difference of squares is. So I have two numbers, let's say positive 3. I know you knew the answer, that's why. Not because I don't want you to answer. And I want your answers. I like your participation, thank you. But you have this situation now where we have x plus 3, x minus 3. We've simplified, not simplified actually, simplification is actually this part. This is simplified, if you think about it, right? This is factoring. I'm actually factoring things out. I'm actually I'm separating the components of that equation out, if you will. But now I have a situation where I have something on the top that looks like something on the bottom. Right, so I have x minus 3 on the top and x minus 3 on the bottom, and anything, if we just were to change this to something that looks like a, right, and the bottom, I can get to this, that looks also like a, and just bear with me when I say a. Who cares what a is, right? If I have a over a, it's 1, right? Any a over a is 1. And remember, I can also express this equation that looks something like this. So x plus 3 times times a over a. Right? I can do that too, like separately. X plus 3 on one side over 1, a over a on this side, right? And if I take x plus 3, multiply it by a over a is whatever a is. In this particular case, it's x minus 3. It's 1. I can eliminate a altogether because it's equal to 1. Anything times 1 is whatever that was, the original equation. So I can actually do something that looks like this, where I kind of kill the bottom altogether, and we have just x plus 3 on the top. So now if I take 3 and sub it in, I have a value of 6. So we can say that the limit as x approaches 3 of x squared minus 9 over x minus 3 is 6. Okay? You're shaking your head, which means you don't know what the hell I'm talking about. Right? But no, so now we get into some tricky situations, right? Because now you have to think about, okay, when I look at this equation, first, let's do my litmus test. Can I sub it in? If the answer is no, and I get something over 0 or something in a square root that's negative or something, you need to do something else in order for you to solve your equation. Okay, that's the first test that you have to do. So again, like it says, we need a little bit of algebra first. Just undo that change. Right, so this will be step 1 here, step 2, and then step 3. I'll put this over here for a second, where we have, again, I'm just going to erase this and do something like, okay, this did not work out to my advantage, where we have this second part here is x plus 3. That's the next part. That's how it simplifies, right? So this is this, then we come to this point where we sub these things out. We actually cross them out. So in a test, or if you were going to write this down, you might just do something like, cross out these values. Oops. Cross out these values on a test. I'm going to cross them out because these things cross out. And then I'm left with x plus 3. And then I know I'm going to a lot of detail here, which you probably can figure out for the most part. People can know what to do. But I want to bring this up because we're going to be talking about this in lab. And then where we get 3 plus 3, we're going to sub in. Finally, we sub in. 3 plus 3. And then, of course, the answer is 6. Okay? Pretty straightforward. I wanted to show you this thing because we may need to go there. Okay? Questions around algebra, and are you still confused? Good. And you're shaking your head because why? Why do we have to do this? Why? Why? That's why you're shaking your head. Because sometimes, we have to simplify an equation. Sometimes when we do a simulation, and this is in like a real-time simulation, it's a serious game. It's not a game where you're playing like, aliens versus player, as an example. And you want to calculate something that's realistic looking, a realistic movement, then we might have an equation that we get because we've calculated it in physics. And we're like, wow, this is a really big-ass equation. Let's simplify it. And we have to do this kind of stuff. Okay, because we want to translate this. Imagine if I translated this equation in to the computer, right? I wouldn't put x squared minus 9. I'd put x plus 3, right? That's the equivalent. All right, so again, everything we've done applies to approaching a limit from one side. This is where we talked about. But sometimes we have a situation where our equation is different depending on which side we're on. So here's kind of a little bit of notation that we would get sometimes, where we say that where the limit as x approaches 1 of f of x, where f of x is equal to these equations. Well, there's 2 equations here now. We have 2 cases, right? The first case is when, let's move the microphone. The 2 cases is when x is actually less than 1. So when x is less than 1, y is always 5. So some kind of stable, thing going on, like a line, right? However, when x is greater than or equal to 1, then y has another formula altogether, another equation, right? And so we have this situation where in this particular case where the equation is not a balanced equation. Okay, we don't have one equation that represents the entire motion, or whatever this thing is, or the entire position, or the entire acceleration graph, whatever the graph is that we're representing, right? So how would this look in Desmos? And can we do this kind of stuff, right? And I think we can, actually. And you may want to try this out if you have your PC with you, right? So again, so we want to say that when x is less than 1, then y is 5, right? So again, one of the things that Desmos allows us to do, is we have some help, I believe, with their graphs. Here we go. Lines, slopes, parabolas, trig. They got us a bunch of cases here, where you can have default graphs. But I believe, if I'm not wrong, that if I wanted to kind of add stuff in, that there is a place where we can get help to do it. And I can't remember. I'm sorry. But example would be that 5, where x is less than 1, right? That's what I want to say. I want to say that y is equal to 5, right? Y is equal to 5 when x is less than 1. Okay, and it says here that we have a bit of a problem. The points are written 1, 2, so it's not going to map. But let's just suppose that we say that x is 5. Is 5, right? Here we go. X is 5 when x is 5. It's actually y is 5. Let's try this out. Y is equal to 5. I used to be able to do this. When x is, of course so. Of course when x is, there's a way of doing it, I think, is with x is less than 1. I think it was something like that. The notation is there. But anyways, at the end of the day is if you have a solid number, like if I put 5 in there, x is equal to 5, right?
But the fields show up below.
Sorry? Oh, there it is. X is equal to 5. I want to put y is equal to 5. But hold on a second here. Yeah, I know. The fields show up below, but I'm not sure if it'll work. That's what I'm saying. If I put in like where x is less than, only where x is less than -1 or -1. 1. There we go. Yeah, it's not going to show up here. It's not less than. It's actually.
If you wrote f of x is equal to
I could do that.
Shouldn't minus, if you want to say.
There's a way. There's a notation, guys. I just don't remember it. I'm sorry, but there's a way. If you guys check it out.
If you want to say y is less than -1, should it be?
Yes, but let me just graph it out with Excel. Sorry, I just don't have time. There's a way of doing it with Desmos, and I'm sorry, I just can't remember. I remember it last year and this year, of course. It's a new year. So let's just map it out. So I have this grid, and let's make it even bigger so you guys can see it. Let's make it 40. Okay. And so here's my grid points, and I'm just going to draw, this equation. Let's just write this in. So when x is less than 1, then y is 5, right? So if I was to draw the points out, and here's a line. No, that's a graph. God damn it. Shapes, line, graph. So this is, for example, here's the line for y, and sure, we'll make that black, and we'll also put the line in for x like this, and we'll make that black as well. And then when x is less than 1, then y is 5. So 1, 2, 3, 4, 5, which is up here. And we'll make another line. So it goes like this: when x is less than 1. So it's going to be not exactly 1, but less than 1. Y is equal to 5, which is something like looks like this. And what we want to do is we also want to put a circle right around, when we draw it, around right here. And it's got to be like this, right? Because it's never going to be 1, right? It's less than 1. So we represent it with this little dot, okay? That's what I wanted to show. But when x is greater than or equal to 1, right? When I say greater than or equal to, this is less than. Greater than or equal to, then I can put the square root of of x or whatever the x is. That's what y is equal to, plus 1. So if I say if it's 1, then 1 plus 1 is 2. Okay, so it's going to be a different graph. So let's just do this out. So again, when it's equal to 1, and when it's 1, 1 plus 1 is 2. So it's here. That's the first point. And I'm not going to graph this out. Let me see if I can graph it out point by point here. You got it working? What'd you do?
Right click. To give a position, right click.
Oh, I would love that instead of me doing it by hand. Tell me how it does.
Right click x less than 1.
So y equals 5.
Okay, so y is equal to 5, and then
Curly bracket
curly bracket right away.
and x is less than 1.
Less than 1.
You're not so broad enough to see it.
What the heck? Oh, there it is. All right, yeah, that's what I wanted. Actually, I drew it wrong, yeah. And then where you can do the same thing where y is equal to square root of x. I think I know how to do the square root. SQRT, root of x, square root of x. God.
The plus 1 is outside the square.
Yeah, I'm going there. I'm going there, brother. Right, there we go. That's what it looks like. So it's kind of a weird thing, right? You have these two pieces of the equation. Whew, that would take a long time.
You didn't have the restraint.
Where x is, y is, thank you for that. Where x is greater than or equal to 1. 1. There we go. Okay, so there you can see that. There are two graphs. They're the same formula, but at different values. It's disconnected. That's the point, right? Whew, that took a long time, like I said. Thank you for that. Thank you for the help. So if you think about this situation, the limit in here, depending on which time you're there, might be different, right? And so you have to approach the limit from one direction or another direction, okay? Whew. So what this means is that I can have a different notation. So I can say that the limit as x approaches a of f of x right? This is f of x in this particular case, right? When we have a complex f of x, right? If the limit as x approaches a from the left side, that's what the negative means, right, is solvable. Okay, this is only means is if this exists, and if as x approaches a from the right side is defined as well. If both of those are defined, then we know that the entire limit as x approaches a is defined. Otherwise, only one side might be defined or the other. Okay, that's what might happen as well. So you have three cases: one where both are defined, limit as x approaches a from one side or the other, and the one, or the case where only one side is defined. If one side is defined, then this doesn't make any sense, right? Because only one side is defined. You can only say the limit from one side. Yes.
They should be defined and they should be equal as well, right?
Well, yes, yeah.
That's what the,
If it's not defined, right, and if it's not equal, then what ends up happening is you have some disconnect. That's what's going on.
that's for our.
Are you good, man? Are y'all good? All right, good.
Because for our example, when x is equal to 1, both cases are actually defined, but they're not equal.
Correct. So
Which means the limit in general is not defined.
this limit here, yeah, exactly. This limit here would be undefined, the way it's written. However, the limit from one side or the limit from the other side, you can get it, right? So the question might be something that looks like this. Okay, does the limit exist? Remember that case we just say. So if I say, does the limit exist? I want to test that both the right side and the left side does exist, and then this limit exists, okay? So how would I do that? Well, first of all, again, do I have to simplify? Yes.
You can tell that on the bottom it's going to be 0, which means
I have to simplify, right? I have
2
to
minus
simplify.
2 is 0, to the fourth is still 0. So if on the bottom it's going to be 0, if you have something over 0, it's going to be it's going to have two separate limits.
Okay, so how about this? We know that 0 is the problem, right? So as the limit approaches 2 from the right, from the right side. So as I go, from this side here, as it approaches positive 2 from the right, and I could separate that out. So x approaches 2 positive from the right side. Does it exist, right? And the answer is, no, it wouldn't, right? Because you get 2, you can see the limit as it goes through, and it doesn't exist because 2 over 2, even if you try to factor this out, by the way, like you'd have, it's 2, it's the power of 4, right? So you have a problem here. And then on the left-hand side, okay, how about from the left? As the limit approaches 2 from the left, does it exist, right? And depending on which side you're coming from, both one side and the other must, kind of equate in some way or the other, right? To the formula. In this case, it does not exist, right? Does that make sense? Because you can't, even if you try to put part out one side or the other, if you try to figure it out, right? As an example, so limit as x approaches 2 from the right, or limit as x approaches 2 from the left. So from the left, so if we were to make this equation happen, right? So negative 5x over x minus 2 to the power of 4. I don't know if we can do that in Desmos, but let's try it. Okay, so 5x over.
I thought this graph, it looks like the limit's negative infinity.
Well, that's the reason, right? X to the power. 1 second here. To the power of 4, right? Okay. I see this where it drops off into oblivion. Yeah. Yeah, same thing. By the way, that calculator, not allowed for the test. It's a graphing calculator. I would have seen it. So notice that this drops off, it's almost like the limit drops off a cliff. Right, see this? There is no definable limit on one side or the other. As it approaches 0, it goes to infinity, right? Like negative infinity, right? Because I have a negative number. So negative infinity is when I have negative some value over 0. Positive infinity is when I have positive some value over 0. Negative and positive infinity, yeah.
But you can define a limit as infinity, right?
Negative infinity is what it is, right? The limit is negative infinity, but I recommend that in your mind, you say to yourself, it's undefined. It's not really defined, right? Yes, you can. But in our case, just for our situation, right? If I was going to plot this out in a computer program, what would be the limit? you could say negative infinity, but what does that mean, you know, in terms of our motion or whatever, right? And I think that it's pretty much going to be unusable. So that's what it does. It then drops off a cliff, right? So this drop off a cliff kind of situation. If I didn't have this negative sign, and if I just took the negative sign away, you can see that it kind of goes up to positive infinity, right? So it's still something over 0. There's nothing we can do for that, right? It goes from positive to, so I'll put the negative sign again, negative infinity. You've got this black hole that happens that sucks up all the numbers, you know, forever and ever. And that's what happens with these two parts of the graph. Is that visual? I mean, I think that helps. For me, it always helped me visualize what happens physically, right, when limits. Okay, so we can say that this is negative infinity. And again, guys, you gotta have to understand what I did here when I did the limits thing, okay? Instead of talking a lot of theory about limits, I put it down to the exact stuff you need for the test, all right? So you understand how limits work, okay? Any questions around limits and why we need them sometimes? Because sometimes, and again, this is the short answer, sometimes we cannot calculate the value or whatever it is, but we're going to get as close to it as possible. As close to it as possible. There was actually a problem that, a classical problem, which is the traveling salesman problem. Anyone ever heard about the traveling salesman problem? It's an algorithm. Yes. You heard about it?
I'm just raising my hand to say I've heard of it.
Okay, so what is it, since you're a smart guy? Tell me what the traveling salesman problem is.
Isn't it like, let's say you have a map of the country and, you know, you have a salesman and he wants to visit a list of cities. It's what is the fastest route that visits all these places?
Kind of, almost there, but you can never go to the same city twice.
Oh, yeah.
That's the trick. See that proviso? I can never go to the same city twice. It's almost, depending on how many cities you have, right? The problem is quite complex. But what if we relax the problem a little bit? We relax the problem, right? And we say, what if he could go to all the cities? What would be his best time? That becomes, and what if he can backtrack, right? That becomes a solvable problem, right? The traveling salesman problem, when I have the bigger the number of cities I have, the more impossible it is to solve, especially if depending on what the root of the cities are, right? It's almost impossible from a pathing perspective. And depending on, especially if the cities are like within a very small area of each other, it's sometimes, or it's something spread out. Or if you give him other parameters, like he must go to this city first and then this city, and then calculate the rest of them, right? It becomes almost impossible to solve. So what limits help us do is in our mind, and this is where mathematics kind of approaches kind of art in some ways, in my opinion. I'm not saying I'm a mathematician. Please don't, I'm not a mathematician. But I see the beauty in it where you can say, what if you simplify the problem and you could solve it? What would be the best case scenario? And that's what limits give us. Best case scenario if we could solve the problem. The other famous one is the secretary problem. Ever hear about that one? All right, this is a really cool one, and it's off topic, but I'll tell you anyway. So you want to find the best secretary for the job. This is a 1950s problem, so please forgive me, the ladies that are out there. This is not suggesting that you're going to be a secretary or anything like that, but this is developed in the 1950s, the algorithm, which was like a businessman wants to find the best secretary possible, so he does all these interviews. When does he stop looking? If he never stops looking, then he would never find the secretary.
He stops looking when he's interviewed every person on earth.
He can't interview every person on earth. It's not reasonable, right? So how would I find the best secretary possible? Well, you limit yourself. You say, okay, the best secretary possible within a time frame, whatever the time frame is, a month, right? Okay, even that's difficult to solve. How do I know I found this best person? And what if, here's the proviso for the best secretary, the best secretary problem, you can't go back. Once you've viewed a secretary, if you interviewed her, you can't pick her. If you go to the next one.
So this is like Deal or No Deal?
Kind of. So imagine this now, right? I can never go back and pick that secretary again. Once I've interviewed her, she's gone, right?
You have to pick them on the spot and that's it.
I can't pick them all on the spot. I can interview one person at a time. These are the conditions, right?
So how do you pick anyone if you can't pick them once you interview?
I have criteria. I have a criteria what makes a good secretary. Maybe it's going to be at the time, 1950s, right? Maybe it was typing speed. Maybe it was the ability for her to write clearly. Maybe it was the way she was communicating. Maybe whatever, some criteria, right? And I have this criteria, except yes?
My idea would be interview a few, get an idea of what the average quality is.
Okay, but
and
then you're
hire the first
sacrificing.
person that exceeds that.
Okay, you could do that, but then those three are gone. So what if you, in those three, this is the question, and there was a condition like that. What if in those three cases, you had already looked at the best secretary, but you passed her by, right? Yes.
You could, I think why not use the Drake equation?
The which one?
The Drake equation.
Okay, yeah.
It's an equation where you calculate the possible chances of life, extraterrestrial life.
Okay, yeah, okay. I understand this. Yeah, you could do the same thing, but you're right. That's probably something you can use, some kind of equation like that. But what if you relax the problem again and you said, I can see the secretary that I've already interviewed again? Then it would be an easier problem, yeah? It's a thinking thing. It's in Japanese, it's called a koan, right? It's like, you want to think about this problem in your mind and how to solve it, right? And you're like, well, it's impossible to solve. I may not find the best secretary ever if I think about this algorithm that I'm running. I can never see the same person twice. I have all these restrictions. But once I relaxed one restriction, it might help me solve the problem. And what scientists, and especially computer scientists do is they relax one of the conditions. Then they put it back. Then they relax the other one. And they put it back. And they try and see what the numbers look like when they do that kind of stuff. And so they get, this is like, it reminds me of Spock. Anyone watch Star Trek at all? Maybe anybody? Nobody? Holy crap. One person, right? Okay, you have a logical person and it's best guess, right? It's like, the computer's going to best guess the closest number that it's going to be, based on your best guess by relaxing some of the parameters, right? Whew. And that's what we do with limits. We relax some of the parameters. We say, we never can get to zero, or we never can get to this number, but we're approaching it. What would it look like? What would the equation look like if we could actually get to that number, right? That's what we're doing. Okay, hopefully I explained that to death. Let's go to the next part. I have this function. Are you good? All right. I have a function. By the way, you're being recorded forever, right? The sneezing is there on YouTube forever and ever.
Wait, where's the camera?
Oh, no one's looking at you, but we're hearing you. So a function, we got this function. We want to find the instantaneous rate of change of some function, the rate of change of position for velocity, the rate of change of velocity for acceleration, the rate of change of whatever, right? And we want it, what happens is we have some function, that rate of change looks like a line tangent to the slope, okay, at that particular point in time, okay? That's what the rate of change looks like, okay? So again, we have some kind of equation and we have this line tangent. And when I say tangent, it's perpendicular to the actual point, that point on the slope of the line, okay? Perpendicular, which means at right angles too, if you think about this, right? So example, at this particular point in time, if I was going to draw a secant line or whatever, or some kind of line, a radius that comes from the middle all the way to whatever this line is tangent to, you would draw, it would look like something that's 90 degrees at this particular point in time. And again, notice the slope is like this. That means that the center point won't be here, it'll be something down here, right? All right, so that's the way we do it. We want to have the slope of the line, if you think about it, or slope of the tangent, right, to find the instantaneous thing. So we have limits, as an example, but we want to get this idea of the average rate of change between 2 points, right? So here's a problem. We talked about the secretary problem. We also talked about the traveling salesman problem, an algorithm that's very popular in algorithms in computer science, right? If you haven't heard these things before, you know what? I recommend take a look at them. Actually, study a little bit of them because it's been a problem where the computer scientists thought about these things in the past. Suppose we have to estimate this instantaneous rate of change of A, whatever A is. Then we can find the slope between A and A plus H, where H is a smaller number, some smaller number. Okay. And we have a graph, I believe, for that. So normally the limits look like something like this. So plus H, right? And we want to subtract the function on this side, and we want to add the function on this side. And as H approaches 0, what would this equate to? All right? If you think about this function where H approaches 0, it doesn't matter what A is right now, okay? But you know that A is the same as this A. If we were to subtract 0, if this would was 0, and let's say a was whatever number, 1, and this was another number 1, and if it was just f of a minus f of a, it would be 0 over 0 in this particular case, would be undefined, because anything 0 over 0 is always undefined. We can't define that. If it's some positive number over 0, it's positive infinity. If some negative number over 0, it's negative infinity.
Well, the limit is.
So that's, but now we're approaching the limit as h approaches 0, right, in this particular case, right? And we want to find the instantaneous number or the slope as h approaches 0, some small number. Okay, and I had a graph here. I think I may have done it later on. Make sure that I didn't do it. So imagine if I want to do this, I want to slice up this line, this graph here. I want to kind of find the average time, if you will, or whatever. What I could do is I could slice up this graph, right, in these little points, right? I can kind of take a number, which we call these little boxes. This is how we used to do it, right? And I can make some other ones, and I can kind of add these little points up. Notice that I have extra information up there, right? So that's not right. And let's look at this one here. I'll start to line off like this. Actually, let's undo that one. And I'll zoom in a little bit so you can see what I'm talking about. So I have this point here. And I want to kind of add all these rectangles up, right, in order for me to find the approximate area under the curve, if you will, right? And this is kind of something like what we do with integrals, and we're going to find this in a second. But this idea of adding all these rectangles up to kind of have an understanding of how we can, kind of simplify the idea of this area underneath this curve, right, is somewhat close to what we're doing to find the instantaneous point. And we'll talk about this in a second.
Can't you just take the limit as the width of the rectangle approaches 0?
We can, but remember we have all these rectangles to add up, multiple rectangles, because we can't. And we have extra information on the top that we're going to chop off.
Yeah, the sum of the limits.
The sum of the limits, yeah. All right, so when we talk about finding the instantaneous velocity or instantaneous anything at a particular point in time, and I'm cutting some of this stuff off. I'm missing a slide. It would have been great if I had that slide, but I have all these tangents to this point. So I have something called a constant function. When I have a constant function, and if I want to find the rate of change as, of x, right? So I kind of look here and I say d over dx. When I see d over dx, I don't want you to look at this as d, but actually delta. I want you to think about this delta over delta x, right? So d over dx, or delta x, the rate of change. That whole part, d over dx, in my mind, I'm thinking the rate of change of c, some constant. What's the rate of change of some constant? 0. It's not going to change. It's a constant. The rate of change. Think about it in your mind what I mean. How often does a constant change? Never, right? If I write a constant and a variable in C++, it's never going to change.
In Louisiana,
right?
they built to change the value of pi to 3.2 exactly. So.
Irrelevant. Let's stay on point. All right. So I have the power rule, right? And here's another one. If I have the rate of change as some x approaches n as some exponent, right? Then we know that what we can do is we can take the exponent, carry it down in front of x, right? And then subtract 1 from it, right? And that would be the answer. So for example, if I had x to the 2, right? Then it would be 2x to the 1. 2x times 2 minus 1 is 2x to the 1, which is 2x. So the rate of change of x to the 2, x to the power of 2, is 2x. That's what we say. And that will be the instantaneous change at that particular x in time. Okay? Again, this is the power rule. We're going to use the power rule a lot. Okay? Here's the multiple rule. Sometimes, just like we did with limits, notice we can remove the constant outside of the rate of change, right, and kind of put it over there. So if I'm multiplying some constant by something else, I can take it out. It doesn't matter also if the sum difference rule, it works out the same ways. If I have two derivatives, derivative of one function and a derivative of another function, I can actually literally separate them to add them or subtract them. Okay, that's the some basic rules. Okay, where it gets funky is when it comes to multiplying and dividing. All right, we'll talk about that in a second. And also the natural log. Log is a weird thing. Okay, so we have the rate of change of f, right? F of x. And we can say that the derivative of an exponent function f of x, where a to the x, is equal to the natural log, or log of a times a to the x. Okay, that's another identity. And some of these you're going to know, some of these you're going to look up and whatever. How about Euler's number? What's Euler's number? Anyone know what Euler's number is? Yes.
2.718.
E, right? It's a fixed constant. It's like pi in some ways. It's a special number in math, right? And would I look up Euler's number in a mathematical, in a math library? Probably not. I would probably put it inside as a constant at the top of my maybe .h file or whatever it's going to be, or a CPP file. And I would always have it available to me.
But if you have a math library already using math, you probably have it.
Yes, but I don't want to always reference it. I want to have it as a constant. And I'd probably cut it down too. I probably wouldn't make it that big. The derivative of the natural exponent of e to the x is itself. So e is a special thing. So when I say e, or Euler's number, right, where I say that the rate of change of e to the x is always e to the x. There's no change. So whatever I put the x e to the 15 is e to the 15, right, as an example. Okay. Okay. This is funky. And this is where we get into, the product rule. When I have two numbers that multiply, so two different equations, kind of g at x, as an example, times, f of x, then what we want to do is, so this situation here, the rate of change of f of x times g at x, right? We can't just say it's the same thing as the rate of change of f of x times the rate of change of g at x. That's not how it works. Because of, right, the derivative of one or the other. We can also call rate of change derivative. The derivative of f of x times the derivative of g at x. You can't do that, right? And the reason for this is because the way derivatives work, right? Wait. So if I have this situation, and by the way, notice that there is this little mark here, that's prime. And whenever I have this mark, prime, it means the derivative of. Okay, that's another way of saying derivative, or d over dx, okay? So if I say f times g, right, some function f times some function g, the prime of the derivative of this is equal to f, the original function, times the derivative of g, right, plus the derivative of f times g, right? That's how it works. So it's not as simple as, it's not a commutative way, just like we did limits. Limits, it's a different thing. Here, when we have derivatives, we actually have to take the derivative of one, multiply by the other, and then add them together, okay? So an example of that would be this, right? I have two equations, remember? And I can handle them separately. What is the derivative of 3x plus 1? Going with the power rule. Okay, so 3x, if you think about anything 3x, x is to the 1, right? 1 minus 1, going back up to the power rule, right? So x to the 1, the answer would be 1 minus 1 would be 0. Anything to the 0 is 1, okay? And then pass down that x in front, right? Well, that means 1. Pass the 1 in front of the 3, right? Because 3x, take 3x is actually written, you could rewrite that as 3x to the 1. Take the 1, subtract them, reduce it by 1, so it becomes 0, right? And then take that 1, multiply it by 3, pass it down in front like this, right? So 1 times 3x, which is 3x, right? That's what it would be, right? But you take the x to the 0 is 1, so the x is eliminated. So it's just 3, right? If I go back down to here, it would be 3. This is a constant, right? We don't care about it. It becomes 0, right? Any derivative of a constant is just 0. We don't have any rate of change of a constant, right? All right, but that's one of them. That's one of the equations. Remember, we have two equations here. So we take the derivative of first, multiply it by the second. So now we take that, 3, multiply it by the whole second equation, okay? And then you take the derivative of the second, and multiply it by the first. And that's how I like to remember it. Derivative of the first multiplied by the second plus derivative of the second multiplied by the first. Okay? So kind of take those two things. So, yeah, let me finish. Thank you. I'll let you know when I need your help. All right? So now if you think about this, what is the derivative of the second? Can someone help me out here? Now you can talk.
Oh, I was just going to say you can even use
I'm asking a question. What's the derivative of the second? Tell me that answer.
5.
Okay, how'd you figure that out?
Because x to the 1 minus 1, x to the 0 is 1.
The second.
1
This
by
is
the 5.
this is the second.
Oh, I thought you meant the second term.
This whole thing. How do I find the derivative of this term? This whole thing.
You just split it up again into the two terms of that.
I could do that. But the easiest way to do is keep it in the bracket. So I take the 4, multiply it by 8, right? That's 32, x to the 3, because I subtract 1 from the exponent, right? Going with the power rule. By the way, guys, we'll handle this in lab in more detail, okay? So if you're lost and you're like, what the hell is he talking about? In lab, I'll go through this in detail, and I'll give you a little exercise to do today to hand in, okay? For bonus marks. And then plus 5, and then because, you know, x to the 1, like you said, is just 5. So whatever this is, so 32x to the third plus 5 multiplied by the first. Now, here's a question. Would I want you to simplify further? If I want you to cross multiply and do all the stuff and give me that simplified version. Unless I say so, the answer is don't simplify. Why? Because I don't care about that stuff, right? I only care that you know how to do the derivatives. The algebra part is not as important for me because it's out of scope for what I'm asking you to do, right? So if you were to take this thing right here and simplify, as an example, and using this equation, right, it would look something like this. So let's just add in a thing. So if I go to here and I go to here, right, the first part would look like this. I would say that, so again, I'm taking the first one, so 3x plus 1. So I'm taking the first, multiplied by the derivative of the second, which is what I just figured out. 32, right, and then see if I can add this in. X to the 3, right, plus 5. And that would be this term. Okay, you see that, right? And then I would put a plus sign, and then I would take the derivative of the first, which is just 3, right? Multiplied by the second, which is this whole equation again. 8 times x to the 4, right, plus 5x. That's the answer. And some of you might say, well, should I simplify this? No. and then, you know, I had some people in my class last year, and they were like, wait a minute. I don't even want to multiply that 3 by the 8x. How, okay, you could do all that stuff. You could collect like terms. You could do all that stuff that you did it. But at the end of the day, I don't need you to take it to that point on a test. If I need you to simplify, I'm going to say simplify to the lowest terms.
So
okay?
This is the form of the answer.
This is the form of the answer that will be sufficient for me. Okay, I don't need you to go further than this. Okay, because this shows me that you know the product rule. Okay, you know the product rule if you show this, because I know that you've taken it to that point. Right, the rest is just algebra. If I was going to simplify it further, I would just take 3x multiplied by 32x to the third, and that would be something like, what, 96x to the fourth, you know, and then that would be the first term. Then I would take the outer terms, 3x times 5 is 15x, right, plus 32x to the third plus 5. And that would be the first, this part right here. And then I would do the same for the second part, yeah.
I just want to double check. So if we do take it further than this,
I'm not going to deduct marks.
oh, okay.
But however, I will be looking for on a test. I'll give you A, B, C, D, E. One of them, I will not simplify. I will take it to this, right? So when you write down your stuff, your steps, if you know how to do it, then you'll have that answer, right? So you're looking at go, wait a minute, okay, so he's not. I might say right on the test question, do not simplify. I'll tell you that, right? Just give me the derivative, but do not simplify. Which this is the derivative. Right, if you think about that, right? But there's no, I didn't simplify. I didn't go to the next step and simplify and put collect like terms and do FOIL on the stuff. I'm not asking you to do that. Okay, you understand? Okay, good. Some people had a problem with this last time. They're like, wait a minute, but this is the same answer. Yeah, but it's not A, B, C, D, or E. I didn't ask for that answer. I said, do not simplify, right? I'm not trying to trick you. I'm trying to make it easier and quicker on a test, right? But people write this whole thing down. They wrote this, like the whole thing. And I saw their test paper afterwards. I'm like, they had the answer, but they picked the wrong one. Why, right? They guessed at the end. They're like, well, nothing equates to this last one, but no, it did up here, right? You went too far, right? So, okay, so that's the product rule. The quotient rule is way more difficult, all right? Because people have to remember this, right? I mean, way more difficult as in, it's hard for people to kind of remember this one. So it's, again, derivative of the first times the second minus, instead of plus, derivative of the second times the first over the second squared, right? That's what it works out to be. And I say first and second as first would be F and second would be G, okay? All right, so how would you do this one? By the way, is it wrong to simplify first? Like an example would be like sometimes, you know, people tend to try and factor stuff out, right? And do this kind of thing first. Try not to do that with derivatives yet. Like try to just use the derivative. So what's the derivative of the top? How would I figure this one out using this equation? And by the way, we're going to have some practice here. Let's just do one, the first one. How do I do this one?
The derivative at the top.
Okay, so let's just write this out. So it would look like, let's do the derivative of the top. So I'm going to do one of these, right? So I have, I'll try and do the top part first. So the derivative of the first, which is this one, the derivative of the top, right? So it would be 3. Let's put it in brackets, right? Times the derivative of the bottom. So 2 times, yeah, the whole bottom. 2 times x to the 2, right? Hold on there. Minus 1, right? Minus the first, which is 3x plus 4, 3x, sorry, minus 4, right? And I'll just write this. I'll write this a little closer to here so you can see it. And then times the derivative of the bottom, which is 2 down to 2 is 4x. That would be the derivative of the bottom, right? So this is the derivative of the bottom, okay? Times the bottom squared. The bottom squared. So it looked like 2 times, this 2 times x, sorry, trying to make this work properly, x to the 2, right, minus 1 squared. That's the answer. See that? All right? So
I'm confused for a second why the first 3 is -1.
okay, so what's the derivative of the first, the top? Derivative of the top is?
3 times,
Oh yeah, sorry. Well, okay, let's look at this, right?
Yeah.
What happens to the -4? It becomes 0.
Oh.
It's a constant, right? It's like saying, take the derivative of 3x. Okay, what is it? 3. What's the derivative of -4? It's a constant, 0.
Yeah,
So
I was just putting 3 minus 4.
right, yeah. It doesn't work like that. So then it's 3, right? And then the whole bottom. That's what this means. That's what G is. The whole bottom, the second, right? And then minus the first, which is the whole first, right? Times the derivative of the second, which is the bottom, right? So 2 times 2 is 4x, and there's no -1, so 4x, right? And then over the bottom square. That's what this is. Now here's a question for you. Could you use the product rule here in this one? Yes.
I mean, you can turn any division into a multiplication
Of?
by multiplying by the inverse.
-1. So you could actually view this as 3x minus 4 times 2x to the second minus 1 all to the -1, right? -1 is 1 over whatever that number is. And if you did that, you could actually use the product rule, and it would give you the same answer, okay?
And you'd have to use the power rule as well.
Yes.
-1.
Okay, does that make sense? So you could view this as, you could multiply to figure this answer out as opposed to use the quotient rule, right? However, the quotient rule is just faster, all right? It's going to give you the same answer at the end of the day, but it's faster than using the product rule more times than not, okay? I'm going to leave this one for the lab, but that's the idea of the way we find the derivative. And remember, the derivative is the instantaneous rate of change of some equation at that point in time. That's what it is. So I want to find the instantaneous acceleration at time 2. Time t is equal to 2. I can use derivative for that. All right. So here's the derivatives of trig functions. We talked about trig functions last week. So, I'm not asking you to forget them this week. Don't forget trig functions. They're still there. But if you notice that, the derivative of sine of x is equal to cos x, right? Derivative of tan x is equal to secant squared x, and so on. Okay, I'm not going to read all these. But these are identities, all right? Do I need you to remember them? No, it's going to be on your cheat sheet, all right? And again, I've drawn these graphs out, which I'll also put on your cheat sheet for you, so that you don't have to remember what cosine and sine look like, the graph of cosine and sine, okay? So you can see that you can help you out understand how, what these values are.
Oh, so you'll be giving us a cheat sheet.
Yes.
Okay.
You might have missed that one. And I think that's it, because I'm going to start doing stuff like find the derivative. These are all questions I want to handle in class, and I'm going to get you guys to answer some of this stuff with me, as we go forward. If you notice, these are some of the problems. Actually, this is kind of where problems and examples start. All right, so how do I do this one? Let's just do one together. How do I do the derivative of f of x, right? And that could also be written f prime at x. How do I find that? Of this. How do I do that? Well, we know that we have 3 different terms, okay? But by the way, people are confused by what I mean by terms sometimes because they've forgotten math, all right? So please forgive me again when I say this, but a term is, one part that you're adding or subtracting or multiplying in the equation. So this would be the first term, kind of. You could look at this as the first term. You could also look at this as the first term, by the way, right? But let's look at this whole thing as the first term, this whole thing as the second term, this whole thing as the third term, okay, if we did that. And if I was going to get the derivative of all this, I could do it separately, right? So what's the derivative of 10x? 10. So that would be that part. So let's just write it out. So we'll do 1, and then we'll stop for the day. And we'll go to lab after this. All right, so again, so first of all, the derivative of this one, x to the 5 times sine of x. What do I need to use there? Product rule. Derivative of the first times the second plus derivative of the second times the first. All right, so let's do that. So derivative of the first times the second. What the heck? Derivative of the first, which is x or 5x. 5x to the 4. Let me just go to format. Okay, design. There it is. 5x to the 4. Derivative of the first, right? Times the whole second, right? Times derivative of the second, so plus. Derivative of the second, sine x. Derivative of sine x is? We just saw it, right? Because it was sorry, it was here. Derivative of sine x is cos x, right? So derivative of the second, so it's cos x, right? Times the first, which is x to the 5. I know this is just more complexity. That's all it is, guys. It's not, oops, x to the 5. And this whole thing, if you think about this, if I took this whole thing here, would be the solution for the first term. All right? Now we're going to do the second term. So minus 3 cos x. We know that 3 times something, right, is we're going to get, you can do the same thing here, minus 3 cos x. So if we did the same thing, and there's another rule that tells us not to do this, okay? But if I was to do the derivative of the first, what's the derivative of 3? So that would be the first term gone, right? Right? Times the second, and then derivative of the second is minus sine x, right? So it's minus sine x, so sine x, right? Multiplied by the first, which is 3. But it's negative. The whole term is negative, right?
So that's going to be positive. Because it's going to be plus, so that's going to be plus sin x. Yeah.
So you can actually do this, right? Minus 3.
Yeah.
Okay. That would solve it. And then that's the second term. Okay, and then we haven't figured this out yet. The next one is plus 10, right? That's the answer. What I want you to simplify from here, if I told you I did. Okay, and you're like, wow, that's so messy, whatever. It's okay. I know what you're doing. I've seen that you know how to do the derivative. The rest is just algebra, all right? The rest is just algebra. Why would I want you to do that? This is not an algebra course. This is a physics for games course. So doing more than this is going to take too long on the test. Leave it here. And it's going to be, you're going to see an answer that looks very similar. The only thing I might do on the answer is kind of say 5x to the 4 sine x plus, cos x, x to the 5 in brackets, minus sine x minus 3. I might put this, I probably won't convert the sign if I can, right? And even if I do, you can figure it out, right, somehow. Plus 10. That's what you'll get on the test. That will be one of A, B, C, D, or E. Guys, the stuff that I'm giving you in lab and in class is going to be eerily similar to the stuff you see on the test. Eerily similar. The formats, the stuff, yes.
Can it be the same?
Sorry?
Can it be the same?
And you do what?
The same equations.
And you...
No, he's asking you if you can give us the same equations during
The exact same equations. Oh, it wouldn't help you, right? Because it's not open book, right? So you wouldn't remember. Most likely. Some of you won't remember. Some of you are.
What if you have like a perfect memory for equations but don't understand math at all?
Well, then you wouldn't be in this course. You'd be in Mensa or something. Okay.
You don't understand math at all.
Doesn't matter. You still be in Mensa. Look at Einstein. He didn't understand math at all. Right? He didn't. He was bad at math, man, but he was able to he was able to perceive. He failed math. He was able.
Urban legend, though.
No. He was able to perceive, the physical world in some 4th dimensions or whatever, right? We can say, and that's an urban legend. Anyway, any questions around limits or derivatives? Because this is the end of the lecture part of today, right? We're going to do the lab part where I actually get you to do stuff. Right now, you don't know why we're doing this kind of stuff, but you'll see it in physics, all right? So please forgive me. I cannot teach you everything to do with limits and derivatives of grade, whatever, I guess it would be grade 11, right? Is when you learn about calculus.
Grade 12.
Was it grade 12?
And we never learned integrals.
We're going to learn integrals next week. And next week is integrals, and we're also going to learn the chain rule. The chain rule is very challenging to learn, and basically what it does is it encapsulates, right, the rules we've already talked about today, right? The product rule and so on, okay? Questions around limits or derivatives? Okay, guys, see you in lab. Please take a look at the assignment number 1. Pair up with people. Does anyone need a partner? That would be a really important thing. Stick around after class if you need a partner, okay? And I'll partner you up, okay? Thank you. I recommend it.
He's going to be on another day.